Welcome to week number 14 for ECE 111, Introduction to ECE. This week we're going to build on what we did in previous lectures and look at filters, filter analysis, and filter design using MATLAB. So a filter is basically any circuit whose gain varies with frequency. That means any circuit that has inductors and or capacitors is a filter. Anything that satisfies the differential equation is a filter. And there's filter design and filter analysis. Filter analysis is kind of what we did last week. Given a circuit, analyze it to find the output. Filter design is design the circuit, find the transfer function differential equation that passes some frequencies and rejects others. So this week we'll look at both of those, analysis and design of filters using MATLAB. Now, before we start, let's give an example. This is a term project from a couple years ago. This is the students built a subwoofer that would pass frequencies below 250 Hertz, reject frequencies above 400 Hertz. So if you click on this link, you get to the YouTube video.
This is a op-amp just to do a 10 times gain. And this is a push-pull amplifier to provide enough current to power the speaker. The output comes out right here. So how this works is this is a third order Butterworth. It's the gain is less than 0.1 for frequencies higher than 300 Hertz, and the gain is greater than 0.9 for frequencies less than 100 Hertz. Alright, so here I have a function generator outputting 75 Hertz here in the input, right here. Also, I have an oscilloscope hooked up right here to this channel, and then I also have this is the output channel hooked up right here. So you can see the the yellow is the input and the blue is the output. Since it's at 75 Hertz, the gain is 1, but also it's amplified by 10. And as I switch the Hertz up here, you can see here, I'll go to 100 Hertz. It's about 0.9. That was our design specs, so it's about 0.9 amplified by 10. And as I continue to go, you can see that it drops. So if I go up to 300 Hertz, you can see it's about 0.1 amplified by 10. So that is our requirements as our design specs. Alright, so we can also sweep from 75 Hertz to 1000 Hertz in 5 seconds, and you can kind of see this is what it does here. You can see it drops off pretty quick. We can hook the sweep up to a speaker so you can kind of hear the output. So you can hear it's getting quieter as the frequency goes up, which is what it's supposed to do. Alright, so here it's at 1 Hertz. You can see that it's got a nice clean sine wave. There's no crossover distortion. It doesn't get stuck in the middle. So now we have it plugged in right there on a computer. It's going to this cord here. This speaker is hooked directly up to the output of the speaker. This speaker actually goes over here through the circuit back to the speaker. So this one's going to be playing the bass, this one's going to be filtered and amplified. This one's just going to be the regular song straight from the computer, so you can hear the difference. We'll just start with just the bass, then we'll add this one so you can hear the difference, then we'll play this one without this one, and yeah, we'll just play around with it. Alright, so here you can see there's the bass. Hook this up. So you can kind of see, try and plug this. So you can see it's clearly passing the low frequencies over here.
So that's an example of a filter, building a subwoofer, something that you cover when you take electronics. Now, differential equations describe filters. Differential equations pretty much describe everything. That's part of the reason you take Calc 1, Calc 2, Calc 3, Calc 4. They're all required. Differential equations are really fundamental. Any circuit with inductors and capacitors are also described by differential equations. That comes from an inductor. The basic equation for an inductor is V is L di dt. For capacitors, I equals C dV dt. And you can derive those from the energy stored, how the energy changes. That's basically how inductors and capacitors work. What that means is that if I have 3 inductors, 2 capacitors, a fifth-order differential equation is needed to describe that circuit. Now, with filter designs, instead of dealing with differential equations, we deal with transfer functions. It makes the analysis a whole lot easier. So suppose I have the following differential equation. It's a third-order differential equation relating x and y. The basic assumption is that all functions are in the form of e to the st. What that does is when I differentiate, I get s, e to the st. So sy means the derivative of y. With that assumption, I can take my differential equation and turn it into an algebraic equation or a transfer function. S means derivative, so third derivative would be s cubed, second derivative s squared, first derivative just y, derivative of x, x. So this is the same thing as that differential equation, just using different notation. What that does is I can factor out the y's, solve for y in terms of x. I get this. This is called the transfer function. It's also the gain. The gain from x to y is a function of s. What that means is this is a filter. If I take a sine wave applied as an input, s changes for each frequency. As frequency changes, the gain changes, is a filter. For example, suppose I have x and y are related by the following transfer function. What's the differential equation? Now we can go either way. Given the differential equation, find the transfer function. Given the transfer function, find the differential equation. Works both ways. To go the other way, here's the transfer function. What I do is cross multiply. Note that s means derivative, so there's the third derivative, second derivative, first derivative, y, first derivative of x, x. So this is the differential equation that relates x and y. And you can use either form, prime notation, and notation used in calculus. They're both equivalent. So, here's the handout. First question problem in the handout. Suppose x and y are related by the following transfer function, or differential equation. What's the transfer function from x to y? Well, you can almost write that out by hand. Again, this is going to be s squared plus 5s plus 8. All that is times y is equal to 2s plus 10 times x. So the transfer function, the numerator is 2s plus 10. Denominator is s squared plus 5s plus 8. That's the transfer function from x to y. It represents the differential equation. I can go the other way as well. Here's the transfer function from x to y. What's the differential equation? Again, I'm going to cross multiply. That's times y. You can almost do that by inspection. That's the second derivative of y plus 6 times the first derivative of y. Plus 5 times y. That's the left-hand side is equal to 10 times the derivative of x plus 20x. So the transfer function means differential equations. Differential equations give you a transfer function. Now, the reason we do that is, here's a problem for you. Suppose I had this differential equation. I want to find y, given that x is equal to, say, 10. Solve for y. Well, what you do back in calculus is I guess the form of the answer, and I'm going to guess y is equal to some constant a. Take the first derivative, second derivative, substitute, first derivative of x, substitute, solve for a to make it match up. Okay, that's not too bad. Suppose x is 10 cosine of 3t. Now solve for y. Now what I would do back in calculus is assume y is in the form of a cosine of 3t plus b times sine of 3t. Take the first derivative, substitute, second derivative, substitute, derivative of x, substitute, match the sine terms, match the cosine terms. 20 minutes later, I get an answer. That's pretty painful. There is an easier way to do it. That easier way uses phasors. What we talked about last week. Here's the gain from x to y. This is true for all s. All I care about is what's the gain at the frequency corresponding to x. Well, if x is equal to 2, this is in phasor form 2. The frequency is 0. E to the 0 is 1. This is 2 times 1, or cosine of 0t. In phasor form, represent x as 2 plus j0. This is the gain everywhere. I just care about what's the gain at s equals 0 times the input at s equals 0. I get a number. That number is the output. Way easier than what you did back in calculus. Repeat if the input is the sine wave. Again, what works at DC also works at AC. I just have to use complex numbers. Now, this is why we study complex numbers. This is why we use complex numbers. This is the gain everywhere. What I care about is what's the gain at this frequency. Here, s equals j3. That's your cosine at 3 radians per second. The input is 2 plus j0. The real part's cosine minus j is sine. So here's the output. This is the gain everywhere. All I care about is what's the gain at 3 radians per second. Times the input at 3 radians per second gives you a complex number. What that number means is the real part's cosine minus j is sine. There's your answer. If you prefer polar form, amplitude and angle, this is the amplitude, here's your frequency, there's your phase shift. Either form is valid. I personally prefer rectangular form for calculations, polar form in lab, but either form works. Notice this is way, way, way easier than what you would do in calculus. And in calculus, it takes about 20 minutes to solve this problem. Using phasors, if you can handle complex numbers, piece of cake. And note that this is a filter. If I change the frequency of the input, I change the output. Instead of being 2 radians per second, suppose the input is 30 radians per second. Same procedure. Here now s is j30. X is 2 plus j0, 2 cosine, 0 sine. This is the gain everywhere. Now just find the gain at 30 radians per second times the input. I get a complex number, real part's cosine minus j is sine. The answer is different because the frequency changed. The frequency changes, the gain changes. That's basically filter analysis. Given a filter with a known input, find the output. That's phasors. That's what we did last week. In MATLAB, I can do that. At DC, s equals 0, x equals 2. Here's the gain times the input. I get a number. That's the DC. At 3 radians per second, here's the frequency. There's the input. Here's the gain times input. Gives you a complex number. Real part's cosine minus j is sine. At 30 radians per second, here's the input. Here's the gain times input. Multiplied together, I get the output. So MATLAB handles complex numbers just fine. That's filter analysis. In MATLAB, there's also a function called TF and eval frequency. I can input the system, the transfer function, into MATLAB using the transfer function. Here's the numerator polynomial in decreasing powers of s. Here's the denominator polynomial in decreasing powers of s. If I want to know what's the gain when the input is 2, the input is 2, the frequency is s equals j0. Gain at s equals 0 times 2 is 7.5. Gain at s equals j3 times 2, first number. Gain at s equals j30 times 2, another number. Same answers we had before. So here's a problem for you. Find the output y for this second order differential equation given that input. So let's pause the video and try to solve that by hand. Okay, picking up. What you would do is the frequency is 5 radians per second, s equals j5. The input is 4 minus j2. The real part is cosine minus j is sine. This is the gain everywhere. I just want to know what's the gain at 5 radians per second times the input at 5 radians per second. I get a complex number. What that means is real part's cosine minus j is sine. So that's one form of filter analysis. If I know the input as a sine wave, I can use phasors to find the output. A second way to do analysis is to do a Bode plot. Now this kind of says, suppose I don't know what the input is, I just know the range, like some sine wave between 0 and 10 radians per second. Find the gain at those frequencies. So here in MATLAB what I do is I just pick a vector, say going from 0 to 20 radians per second, steps every 5. S is j omega. The gain is the way you type it. It's 10s plus 30 over s cubed plus 4s squared plus 6s plus 8. That's the gain at each of these points. Then plot them. And note I'm using dot notation. MATLAB is a matrix language. This is a matrix. If I do slash or power, it's going to try to take a matrix division. I don't want to do that. I want to treat these as separate numbers. That's what dot slash does. It tells MATLAB, don't treat this as a matrix. Treat these as separate calculations. Do each one separately. When I do that, I get the gain at each frequency, making the step size smaller to make it a smoother plot. Here's my frequencies going between 0 and 10 radians per second. S is j omega. Here's the gain. Plot frequency versus magnitude. And I get this plot. A couple things to note. I plotted the magnitude of g. G will be complex numbers. That confuses MATLAB. If I plot x versus a complex number, MATLAB doesn't really know what to do. I've got x-axis is time, y's got one dimension, but I've got 2 degrees of freedom, real and complex. So what MATLAB does, if I plot a complex number, it just plots the real part. Again, not knowing what else to do. That's not what I want. I want to plot the magnitude. So that's what this does. Plot omega versus the magnitude of the gain. What the magnitude tells you is this is a filter. As frequency changes, the gain changes. This tells you this is the low-pass filters. Low frequencies are passed, high frequencies are rejected. This passes frequencies below 2 radians per second, rejects frequencies above 5-ish. And there's the thing called a resonance. If I hit this frequency, like 1.5 radians per second, I get kind of a booming sound. So have you ever heard the term boombox? That's what this refers to. If this is a speaker, it booms when the bass guitar hits that frequency right there. Hence the name boombox. That's what this tells you. It's a graphical way to say what the gain is versus frequency. Change the frequency of the input, I can get high gain, really big gain, then attenuation. Now G is a complex number. It's got a real part, complex part, has an amplitude, has an angle. I could plot the angle versus frequency as well. I personally don't know what that tells you, but it's something. Normally I just plot gain. I know what gain means. I'll have a large signal, small signal. That's what I can hear. I personally can't hear phase. Some people say they can. I can't, so I kind of ignore phase. Normally you don't care about phase. Occasionally you do. If you ever care about it, it's available for you in MATLAB. So that's filter analysis. Second problem, something also covered in electronics, is how do you design the filter? So this is covered in signals, electronics. I think it's covered in circuits too. How do you design a filter to give you some desired gain versus frequency? Now, you'll get to that when you take circuits 2, electronics, signals. In this class, what we're going to use is MATLAB. One of the great things about MATLAB is if you know nothing about filter design, you can do a pretty good job just designing filters using MATLAB. What we'll be using is a function called fminsearch. Now, a typical way to design a filter is like this. I want to design a filter that passes frequencies between 1 and 3 radians per second. Pass means the gain is somewhere between these 2 points. I want to reject frequencies above 5 radians per second, so these are out. Come up with some filter that does this. That's filter design. And we're going to use fminsearch to design that. So a little bit of background on fminsearch. We talked about this before, but we'll repeat that. fminsearch is a way to find a minimum of a function. So for example, suppose I want to find out what is the square root of 2. I'll create a function whose minimum is returned when I hit the square root of 2. So this is the error. If I take x squared minus 2, this is x squared minus 2. I want to find the zero crossings. There's the solution. There's another solution. fminsearch doesn't find the zero crossings. It finds the minimum. So if I take the error and square it, what I get is this type of function. That's error squared, or j. fminsearch will then find these points. Now in MATLAB I can do that. If I find, here's a function called root 2. This is a function I wrote. I'm going to pass my guess for the square root of 2. It returns the squared error. So I say, is the root of 2 6 or 5? So here's my guess. This is the error, 23. There's j, error squared. Is the square root of 2 4? Cost got smaller, it's closer. Is it 3? Is it 2? I can now use fminsearch. Say ZE is fminsearch. Here's my function, root 2. Here's my initial guess, 5. And it then iterates, tries to find what value of Z minimizes j. It says the best I can do is 1.4142, and there's the sum squared error. Basically 0, so that's the square root of 2. And note that the answer I get depends upon my initial guess. There's another solution close to minus 1.4 to make this my initial guess minus 5. It's going to converge somewhere. In this case, it converges to the other solution, minus 1.414. So there I found the square root of 2. You're probably not real impressed. It's not that hard to find. Let's do a harder problem. Let's find the shape of a hanging chain. Now what chains do is they minimize the potential energy. So what shape minimizes the potential energy? Given the constraint that the length is 12, and the left endpoint is at 0, the right endpoint is at 0, 10 meters apart. Well, using fminsearch, I can find that. I can find that by calculating, but you need to take calculus of variations. That's a course, about 2 courses after differential equations. Or, knowing nothing, use MATLAB. So here's my function. I'm going to guess the shape of the chain. It's going to return the sum of y, that's the potential energy, and the length of the chain, length needs to be 10, or 12. There's my cost. What shape minimizes the cost? In MATLAB, I can do that. So here's my cost chain. If I say, is it minus 1, 2, 3, 4, 5, 6, 7, 8, 9. If that's my guess, there's the shape of the chain, there's the cost. Can I do better? Let's try that. Now the cost is minus 4. I can guess again, or let MATLAB guess for me. So I want to minimize this function. Here's my initial guess. And it's going to sit there and iterate, try to show you or calculate the shape that minimizes your cost function. And it's kind of fun to watch. The way I'm able to graph this is I plot the data, pause for 10 milliseconds, and then continue. This really slows it down, but it's kind of fun to watch. So it's iterating, trying to find an answer. We'll let it go for a bit. And there you go. That's actually hyperbolic cosine, the shape of the hanging chain. Let's use that to design a filter. So kind of like that bass boost, I want to build a low-pass filter. In this case, pass frequencies below 3 radians per second, reject frequencies above 3. Come up with a filter that does that. Now to do that, I need to give it some parameters to guess. I'm going to guess the form of the filters in this form. I have A, one set of complex poles, second set of complex poles. I'll then take the frequency response of what A, B, C, D, E mean versus what it should be, calculate the error, return the sum squared error, find A, B, C, D, E to minimize the sum squared error. So here's the function of MATLAB. I'm going to guess A, B, C, D, E. Admin search wants just a single parameter to be passed, but that can be a vector containing 5 terms. That's what those 5 terms mean. Let's take the frequency between 0 and 10 radians per second. S is j omega. Here's what the gain should be. Gain should be 1 out to 3 radians per second. Here's what g of s really is. Take the difference in the gains, return the sum squared error, and plot it. So here's what that looks like. Here's my filter, cost f. So that's my 5 gains. Here's what the gain should be. Here's what my filter is. There's the sum squared error, 27. Can I do better? So let's try 5. It's better. Let's make this one s squared plus s plus 1, s squared plus s plus 10. Better. And guess again, or let MATLAB guess for you. So to minimize the function cost f, here's my initial guess. And I'll sit there and vary the 5 parameters, vary A, B, C, D, E, until I can't do any better. And there it says, that's the best I can do. This is your A, B, C, D, E, sum squared error. Now with admin search, sometimes it kicks out due to max iterations. Sometimes it kicks out because it found the best it can do. If I say pick up where you left off, keep going, kind of make that cost 0.9575 smaller. The answer is nope, that's the best it can do. So when I'm done, here's my answer. What that means, that's A, B, C, D, E. There's my numbers A, B, C, D, E. That's the best filter. And here's gain versus frequency. What's pretty cool is using fmin search, I just designed a low-pass filter, knowing nothing about filter design. When you get to electronics and signals, you'll be designing filters by hand. But for now, in this class, knowing nothing about filter designs, I can have MATLAB design a pretty good filter for me. Turns out this is actually a Chebyshev filter, something you'll talk about when you take electronics. And the filter isn't arbitrary, but look at where the poles are. Again, I've got one set of poles right here, the second set of poles right there. Plot them. Here's where the poles are. Here's the complex part, complex part, real part. This is on an ellipse. I basically scatter the poles around the passband region. And what that does is, for frequencies between minus J3 and plus J3, I get these resonances. When I'm close to a pole, I get a resonance. There's the first pole, resonating at J 2.57 radians per second. Second pole, resonating at J1 radian per second. Its conjugates, then drops off. That's something we'll be doing when you take signals in systems and electronics, design a low-pass filter. Kind of what the students did in the previous video. They designed a low-pass filter to pass frequencies below 250 Hertz to build a subwoofer. Then you got your filter design. Once I have the filter design, now design an op-amp circuit to implement it. But we'll leave that for when you take electronics. Now, what's pretty neat about fmin search, if I change the desired response, it can sit there and move the poles and zeros around to match that with this gain versus frequency. So just kind of arbitrarily, not sure why you'd want to do it, but if I want to have this gain versus frequency, I can design it using fmin search. Here I'm going to have 7 degrees of freedom, A, B, C, D, E, F, G. My desired response I can do as a piecewise linear function. Between 0 and 3 radians per second is this line. That's the gain between 0 and 3. Between 3 and 6, this is the gain. Here's the equation for that, valid between 3 and 6 radians per second. And kind of the way I get that, this is the slope. Change in y over change in x is the slope. At x equals 0, I should get 0.2. Here the slope is change in y over change in x. The slope is minus 0.2. Plug in a number, like at 3 radians per second, the gain should be 1. Gives me a G ideal. Come up with a function in MATLAB. I'm going to add 2 more terms. There's a G in there as well. I guess there's not 6 terms. Here's my ideal response. There's my actual response. Calculate the difference in the gain. Return the sum squared error. All stays about the same. Kind of show you how that works. Here's the function in MATLAB. From the command window, I can call it. Step 2. Choose the numbers 1, 2, 3, 4, 5, 6. Here's the ideal response. Here's what I actually have. Try different numbers. Let's have a pole at 1, s squared plus s plus 2, s squared plus s plus j3. 9 times 4 is 36. Just kind of taking a guess. Play with the numbers to get something close. Guess, guess again, guess again. I can try it that way. Or let MATLAB guess for you. So that's my initial guess. It'll sit there and play around with the 6 parameters. I can see here's the pole, the real pole, first complex pole, second complex pole. It's playing around with the real part, the complex part, trying to make it so that the net result matches up my desired response. So it's trying. Guess it's a whole lot faster than I can guess. And it'll kick out either due to max iterations or because it can't do any better. Here it actually kicked out due to max iterations. It's not done. I can tell it to pick up where you left off. Keep going. Can I make the sum squared error less than 1.755? It runs for a while. Eventually kicks out an answer. Here's trying to guess by hand. Let fmin search run, and eventually kick out the answer. The sum squared error is 0.52. There's the gain versus frequency. Not perfect, but given the constraints, that's the best I can do. And here's your parameters, A, B, C, D, E, F. If you're taking electronics, it would then be, okay, now let's design an op-amp circuit to implement that. But that'll be a later course. Here we're just happy. I've got A, B, C, D, E, F. What that means is that's my transfer function. That's filter design. So filters are something that you cover when you get to electronics, signals and systems, circuits 2. And with filters, you have filter analysis and filter design. A filter is pretty much any circuit where the gain depends upon frequency, which is any circuit with inductors and or capacitors, or anything that's described by a differential equation, which gives you a transfer function. Filter analysis is actually pretty easy with complex numbers. I just take the transfer function, plug in S equals j omega, and then use phasors to represent the input and output and calculate. Output is gain times input. That's filter analysis. Filter design is a lot harder. You need to design, place the poles, place the zeros to give you your desired frequency. And the pattern is you place poles by frequencies you want to pass, place zeros by frequencies you want to block. And that's something that you cover when you take electronics and signals and systems. In this class, I can do a pretty good job designing filters using MATLAB's fmin search. So MATLAB is basically a really useful program. I can solve all sorts of problems with MATLAB. Filter design is one of the problems you can solve. And that is lecture number 14 for ECE 111, filter design using MATLAB.